Nuclear fusion, often referred to as the holy grail of energy production, holds extraordinary promise for advancing space propulsion. The principles of fusion are nothing short of captivating. Inside the hearts of stars, fusion occurs when hydrogen nuclei merge under immense pressure and scorching temperatures, creating helium and unleashing colossal amounts of energy. This very process powers our sun, the energy source that sustains life on Earth. Today, scientists are delving into ways to harness this stellar process to develop spacecraft propulsion systems that could revolutionize space exploration, enabling us to reach distant planets and even venture beyond our solar system. One of the most exciting prospects of fusion propulsion is its potential to achieve speeds near the speed of light. If a reliable fusion reactor could be built, spacecraft might drastically reduce travel times across the solar system and even to neighboring star systems. This raises an exciting question. How could fusion propulsion systems function in practice? Several innovative designs have been proposed, including the fusion rocket. This concept involves using the immense energy from fusion reactions to heat a propellant, such as hydrogen, and then expelling it at incredible speeds to generate thrust. Unlike conventional chemical rockets, fusion propulsion could offer continuous acceleration, a game-changing feature for deep space travel. The fuel source for fusion is another fascinating aspect. Fusion primarily relies on hydrogen isotopes, deuterium and tritium. Deuterium can be extracted from seawater, while tritium can be bred from lithium, which is available on Earth and potentially on the Moon or asteroids. These resources offer a sustainable fuel supply for long-term space missions, reducing the need to launch massive amounts of material from Earth. However, replicating controlled nuclear fusion remains a monumental challenge. Projects like ITER in France represent a collaborative international effort to create a functioning fusion reactor. If successful, this groundbreaking technology could pave the way for similar applications in space travel. Despite its potential, the development of fusion propulsion systems faces technological and safety hurdles. Unlike nuclear fission, which generates long-lived radioactive waste, fusion produces minimal and mostly harmless byproducts. Nevertheless, safety concerns remain, particularly regarding potential reactor malfunctions in space. Engineers are tasked with designing systems that remain secure under the harsh conditions of space travel. Fusion, the celestial force that powers the stars, involves merging two light atomic nuclei into a heavier one, releasing immense energy. On the Sun, hydrogen nuclei fuse to form helium, radiating energy that sustains life on Earth. Scientists have long sought to replicate this natural phenomenon on Earth to provide a clean and virtually limitless energy source, meeting global energy demands while reducing environmental impact. The greatest challenge lies in recreating the extreme conditions necessary for fusion. To trigger the reaction, temperatures must soar to around 150 million degrees Celsius, 10 times hotter than the Sun's core. To achieve this, researchers employ powerful magnetic fields to confine plasma, a state of matter where electrons are separated from nuclei. Magnetic confinement fusion, with devices like tokamaks and stellarators, leads this cutting-edge research. Another promising approach is inertial confinement, a method that uses intense bursts of energy to compress and heat the plasma. Fusion involves using powerful lasers to compress small pellets of fuel to achieve the necessary conditions for fusion. The National Ignition Facility in California is one of the leading research centers using this method, aiming to create a self-sustaining fusion reaction. Despite the technological challenges, recent advancements have shown promising results, bringing scientists closer to the goal of achieving net energy gain from fusion reactions. Countries around the globe are investing in fusion research, with notable international collaboration on projects like ITER, the International Thermonuclear Experimental Reactor, being built in France. It aims to demonstrate the feasibility of fusion as a large-scale energy source, and is expected to start its experiments in the coming years. By proving that fusion can produce more energy than it consumes, ITER will pave the way for future fusion power plants. The potential benefits of nuclear fusion are immense. Unlike fossil fuels, fusion produces no greenhouse gases and generates minimal long-lived radioactive waste. Furthermore, the fuel for fusion, such as isotopes of hydrogen like deuterium and tritium, is abundant and can be extracted from water. This means that fusion could provide a sustainable energy source for generations to come, significantly reducing our reliance on fossil fuels and contributing to the fight against climate change. Nuclear fusion, the process that powers the stars, including our own sun, occurs when two light atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy. This reaction typically involves isotopes of hydrogen, such as deuterium and tritium, which under extremely high temperatures and pressures overcome their natural repulsion due to their positive charges, allowing them to fuse together. The fusion process in stars is a natural occurrence, where the immense gravitational pressure and heat within a star enable this reaction to take place, converting mass into energy, as described by Einstein's famous equation E equals mc squared. In contrast, nuclear fission is the splitting of a heavy atomic nucleus into two or more lighter nuclei, releasing energy, neutrons, and gamma rays. Fission, which is currently used in nuclear power plants, requires much lower temperatures than fusion, making it easier to control. However, it produces long-lived radioactive waste and poses risks of catastrophic accidents. Recent advancements in fusion research focus on methods such as magnetic confinement, which uses powerful magnetic fields to contain hot plasma, and inertial confinement, which compresses fuel pellets with lasers. These approaches aim to replicate the conditions necessary for controlled nuclear fusion, which could revolutionize energy generation on Earth. Fusion's potential extends beyond power generation. It is considered a promising source of propulsion for space travel, as it can produce vast amounts of energy from relatively small amounts of fuel. This could enable spacecraft to travel faster and farther than ever before. Researchers are exploring concepts like fusion rockets, which could use magnetic confinement systems to contain plasma and direct energy to create thrust. Such technologies could significantly reduce travel times to destinations like Mars, or even enable interstellar exploration. In summary, nuclear fusion holds incredible promise as a clean, nearly limitless energy source. It has the potential to transform how we generate power, reduce greenhouse gas emissions, and enable advancements in space travel. Despite the challenges in achieving and maintaining the extreme conditions required for fusion, ongoing research and international collaborations like ITER bring us closer to realizing its potential for the benefit of humanity. As we look at the historical context of space exploration, the mid-20th century marked a notable turning point with the launch of Sputnik by the Soviet Union in 1957. The world watched as humanity took its first steps into the realm of space travel, igniting the space race between the United States and the Soviet Union. This competition led to significant advancements in technology and science, culminating in the Apollo 11 mission, where astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the moon in 1969. Research into nuclear fusion, the process that powers the stars, began in the early 20th century. Scientists were intrigued by the idea of harnessing the energy produced by fusing atomic nuclei, which could potentially provide a limitless source of clean energy. The groundwork for nuclear fusion research was laid by several pioneers, including physicist Hans Bethe, who played a crucial role in understanding how hydrogen nuclei fused to form helium in stars, releasing incredible amounts of energy. Bethe's work, which earned him the Nobel Prize in Physics in 1967, was instrumental in explaining the mechanisms of stellar nucleosynthesis, the process by which stars create heavier elements through fusion. During the same period, Other scientists like Edward Teller and George Gamow contributed significantly to the theoretical understanding of fusion. Teller, often referred to as the father of the hydrogen bomb, explored fusion as both a natural process in stars and a potential means to create powerful weapons. Meanwhile, Gamow, a prominent physicist and cosmologist, examined the implications of fusion in the context of the Big Bang and the early universe, further enhancing our understanding of how elements are formed. By the 1950s, research into nuclear fusion shifted toward practical applications, particularly in the context of energy generation. Devices like the tokamak, a type of magnetic confinement system, were developed, spearheaded by scientists such as Igor Tamm and Andrei Sakharov in the Soviet Union. The tokamak design became one of the most promising approaches to achieving controlled nuclear fusion, leading to extensive research efforts in countries including the United States and Europe. These projects aimed to replicate the conditions found in stars, where immense pressure and temperature allow fusion to occur. In the decades that followed, fusion research evolved with various experiments and projects exploring sustainable fusion reactions. The 1980s saw the establishment of large international collaborations, such as the Joint European Torus (JET) project in the UK, which investigated the feasibility of fusion as a viable energy source. Today, the quest for practical nuclear fusion continues with ambitious initiatives like ITER, International Thermonuclear Experimental Reactor, involving scientists and engineers worldwide striving to make fusion energy a reality. This effort taps into the same reactions that fuel the sun and aims to transform our energy landscape. Early research on fusion's potential for space exploration emerged during the mid-20th century. Concepts like Project Orion in the late 1950s proposed using nuclear explosions to propel spacecraft, while later designs such as Project Daedalus, developed in the 1970s, envisioned fusion reactors capable of propelling spacecraft to nearby stars. These designs highlighted the immense potential of fusion energy for interstellar travel, though significant engineering challenges remained. Fusion-driven propulsion systems, such as the Direct Fusion Drive, DFD, have been proposed to combine traditional rocket technology with nuclear fusion. By heating a propellant, using a fusion reactor, and expelling it to produce thrust, such systems promise much higher efficiency than conventional chemical rockets. In the 1980s, hybrid concepts like the Helios spacecraft, which combined solar and fusion energy, demonstrated innovative ways fusion technology could support space exploration. In conclusion, whether in advancing energy generation or enabling interstellar travel, nuclear fusion remains a transformative scientific frontier. As humanity continues its quest for innovation, fusion promises to play a central role in shaping our future, both on Earth and beyond. Carefully designed and controlled, as any instability can lead to the plasma touching the reactor walls, causing energy loss and damage to the reactor itself. On the other hand, inertial confinement works on a different principle. In this method, small pellets of fusion fuel, typically a mix of deuterium and tritium, are rapidly compressed and heated using powerful lasers or other forms of energy, such as X-rays, to achieve the necessary conditions for fusion. The idea is to create a shockwave that compresses the fuel to extremely high densities in a very short time, often just a few nanoseconds. Facilities like the National Ignition Facility in the United States focus on this technique, aiming to achieve the right conditions for fusion by delivering an enormous amount of energy in a very brief burst to the tiny pellet of fuel. The rapid compression raises the temperature and pressure to levels where nuclear fusion can occur, allowing the fuel nuclei to overcome their natural repulsion due to their positive charges. While both methods aim for the same ultimate goal of achieving sustainable fusion reactions, they rely on fundamentally different physical principles and technological approaches.
Magnetic confinement seeks to maintain a stable plasma for longer periods of time, which can lead to continuous energy production, while inertial confinement focuses on achieving fusion in very short, intense bursts. Each method presents its own set of challenges. For instance, magnetic confinement requires maintaining stability over time, complicating the design and operation of the magnetic fields. In contrast, inertial confinement must achieve precise timing and energy delivery to successfully compress the fusion fuel. Researchers are continuously working on both fronts, exploring improvements in their respective technologies and seeking to overcome the technical hurdles that have so far prevented practical fusion energy from becoming a reality. The pursuit of fusion energy, with its potential for providing a nearly limitless and clean source of power, remains one of the most significant challenges in science and technology. Fusion propulsion, often seen as the holy grail of space travel, requires several key technological advancements to become feasible. These advancements are not just incremental improvements, but groundbreaking innovations that could change the landscape of how we explore the universe. First, we need significant developments in fusion reactor technology itself, specifically in creating and sustaining a controlled fusion reaction that can produce more energy than it consumes, a challenge that has puzzled scientists for decades.
Traditional methods like magnetic confinement, seen in projects like ITER, need to evolve, improving their efficiency and stability. This may involve new materials capable of withstanding the extreme conditions within a fusion reactor, such as high temperatures and radiation. Second, advancements in superconducting materials are essential, as they would allow for more efficient magnetic confinement systems, reducing energy loss and making it possible to maintain the high magnetic fields necessary for fusion reactions. Additionally, we need to enhance our understanding of plasma physics. The behavior of plasma at the temperatures required for fusion is complex and not fully understood. Researchers are exploring advanced computational models and simulations to predict plasma behavior more accurately, which is crucial for developing reliable fusion systems for propulsion. Another area that requires innovation is the development of lightweight, efficient engines that can harness the energy produced by fusion reactions. This means creating propulsion systems that can convert the thermal energy from fusion into thrust effectively, perhaps through novel mechanisms such as direct energy conversion, which could drastically improve spacecraft performance. Moreover, we need advancements in fuel sourcing. Current fusion experiments mainly use isotopes like deuterium and tritium, which may limit scalability and sustainability. Finding alternative fuels, such as helium-3, could open new possibilities, especially if we can source them from lunar regolith, enhancing the feasibility of fusion propulsion for deep space missions. Furthermore, the integration of advanced robotics and AI in managing and maintaining fusion reactors will be crucial. These technologies can help monitor the complex systems involved and make real-time adjustments to ensure optimal performance. Lastly, the development of robust safety protocols and containment systems is vital. Any fusion propulsion system must ensure safe operation, especially when dealing with immense energies. This includes building redundant systems and fail-safes to handle unexpected scenarios, ensuring the technology can be trusted for both crewed and uncrewed missions. All these advancements work together, creating a comprehensive framework that will enable fusion propulsion to become a reality, propelling humanity farther into the cosmos and unlocking new frontiers. In recent years, the field of space exploration and research has been bustling with groundbreaking developments, pushing the boundaries of our understanding of the universe. One of the most exciting areas of current research is the study of exoplanets, which are planets outside our solar system. Scientists are using advanced telescopes, such as the James Webb Space Telescope, launched in late 2021, to examine the atmospheres of these distant worlds, searching for signs of water vapor, carbon dioxide, and other molecules that could indicate the potential for life. This research is crucial as it helps us to understand not only the possibility of life beyond Earth, but also the conditions that allow planets to support life, guiding our search for habitable environments in the cosmos. Another significant focus of current research involves the study of dark matter and dark energy, which together make up about 95% of the universe, yet remain largely mysterious. Astrophysicists are conducting experiments using particle colliders and large observatories, such as the Large Hadron Collider in Switzerland and the Vera Rubin Observatory in Chile, to gain insights into the fundamental nature of these elusive components of the universe. Understanding dark matter and dark energy could revolutionize our comprehension of the universe's formation, expansion, and fate. As researchers delve deeper into these topics, they are also exploring the potential for new physics beyond the current standard model, which describes the fundamental particles and forces in the universe. In addition, the quest for a deeper understanding of our own solar system has led to exciting missions such as the ongoing study of Mars through the Perseverance rover. This rover is actively collecting samples and searching for signs of ancient life. Equipped with advanced technology, including a suite of scientific instruments, it is designed to analyze rock and soil samples, paving the way for future human exploration of the red planet. Moreover, missions to the outer planets, like NASA's Europa Clipper, aim to explore Jupiter's moon Europa to investigate subsurface oceans that could harbor life. This makes the exploration of icy worlds a priority for astrobiology research. Another area of great interest is the development of space technology, particularly in propulsion systems. Researchers are investigating innovative technologies such as ion thrusters and nuclear thermal propulsion, which could revolutionize space travel by reducing travel times to distant planets and making deep space exploration more feasible. These advancements could enable future missions to places like Mars or even the outer planets. In recent years, the field of nuclear fusion research has made remarkable strides, particularly in its potential application for space propulsion, which could revolutionize how we travel beyond Earth. One of the most exciting breakthroughs comes from successful experiments conducted by the National Ignition Facility, NIF, at Lawrence Livermore National Laboratory, where researchers achieved a significant milestone known as ignition. This means they produced a fusion reaction that released more energy than was input into the process, a crucial step toward making fusion a viable energy source. The implications of this for space travel are profound, as nuclear fusion could provide a nearly limitless source of energy, enabling spacecraft to travel faster, farther, and more efficiently than current chemical propulsion methods allow. Private companies such as Helion Energy and TAE Technologies are also pushing the boundaries of fusion technology. Helion Energy is developing a unique approach called pulsed fusion, aiming to create compact fusion generators that operate efficiently and affordably. TAE Technologies focuses on achieving stable plasma confinement, vital for sustaining fusion reactions long enough to generate usable energy. Researchers at the Massachusetts Institute of Technology, MIT, have also been exploring the use of fusion as a propulsion system for interstellar travel, with concepts such as the direct fusion drive. This innovative system proposes using fusion reactions to create thrust directly, potentially allowing a spacecraft to reach significant fractions of the speed of light. Such speeds could open the possibility of reaching nearby star systems within a human lifetime, making interstellar travel seem more achievable than ever. Advancements in material science play a crucial role in this research. Developing materials that can withstand the extreme conditions inside a fusion reactor is essential. Innovations in superconductors and advanced ceramics enable the construction of more efficient reactors, which are vital for both energy generation and propulsion systems. Efforts to create fusion reactors that operate continuously rather than in short bursts are ongoing, with global teams working on designs to enable practical applications in space. Organizations like NASA and the Princeton Plasma Physics Laboratory are leading research into plasma physics and fusion energy, focusing on energy generation and its potential applications for propulsion in space. On an international scale, CERN and private companies like Helion Energy are emerging as key contributors, driving innovation in fusion research and its adaptation for spacecraft. Experimental fusion reactors, designed to replicate processes powering the Sun, are advancing our understanding of propulsion systems. Fusion propulsion, utilizing the energy produced in fusion reactions, could achieve higher thrust-to-weight ratios, drastically reducing travel times. For example, a fusion-driven rocket could reduce the journey to Mars from several months to a few weeks, a monumental leap in space exploration. The behavior of plasma, the fourth state of matter consisting of charged particles, is a critical aspect of developing fusion propulsion systems. Research into plasma confinement and control within fusion reactors provides valuable insights into making fusion propulsion viable. Additionally, advancements in magnetic confinement and laser-based fusion techniques are opening new possibilities for spacecraft acceleration. Fusion propulsion offers numerous advantages, including high efficiency, reduced travel times, and cleaner energy generation compared to chemical rockets. Utilizing isotopes of hydrogen abundant in seawater, fusion systems could allow spacecraft to refuel during journeys, enabling long-term exploration. Furthermore, fusion reactions produce minimal harmful byproducts, primarily helium, making them a cleaner and more sustainable option. The continuous thrust capability of fusion engines enables smoother acceleration and deceleration, enhancing mission flexibility and astronaut comfort. Fusion propulsion is also safer than traditional nuclear propulsion systems, as it does not produce long-lived radioactive waste, significantly mitigating environmental risks. As research and development continue, the potential of fusion propulsion to transform space exploration is becoming increasingly clear. With advancements in material science, energy generation, and plasma physics, the dream of interstellar travel is moving closer to reality, setting the stage for humanity's next great leap into the cosmos. Companies, which can take years to secure. Additionally, there are ongoing costs related to maintenance, Zrania infrastructure, and the deployment of these systems once developed. One of the main driving forces behind the interest in nuclear fusion propulsion is the potential for vastly reducing travel time to distant star systems. Current propulsion methods are limited in speed, and reaching even the closest stars would take tens of thousands of years with current technology. Fusion propulsion promises the possibility of interstellar travel within a human lifetime, which is an exciting prospect for future space exploration. However, achieving this vision requires solving numerous technical, safety, and regulatory challenges. The promise of fusion propulsion lies in its potential to generate immense amounts of energy through the fusion of atomic nuclei. This reaction, which powers the Sun, has the potential to provide nearly limitless energy if it can be harnessed in a controlled environment. The challenge is ensuring that the fusion process can be sustained long enough to produce useful energy for spacecraft propulsion while keeping the system safe and reliable. Achieving a self-sustaining fusion reaction, known as ignition, is one of the key milestones in developing fusion propulsion technology. In conclusion, while the concept of nuclear fusion propulsion holds great promise for future space exploration, it is not without its challenges. The development of fusion propulsion systems will require significant advancements in technology, engineering, and safety protocols, as well as substantial investments in research and development. However, with the continued progress in fusion research, there is hope that one day we will have the capability to explore distant star systems and beyond, opening up new frontiers in human space exploration. Companies, all of whom seek to understand the potential IAL returns on their investments, are facing the challenge of long timelines and the inherent risks involved. Moreover, the economic viability of fusion propulsion hinges on the operational costs associated with maintaining and running fusion reactors. Unlike conventional chemical rockets, which rely on fuel that can be costly and finite, fusion propulsion promises to utilize abundant resources such as deuterium and helium-3, both isotopes of hydrogen found in seawater and on the Moon, respectively. This could lead to significantly lower fuel costs in the long run. However, the technology must first prove its ability to produce energy efficiently and reliably, which remains a significant hurdle. The potential for fusion propulsion extends far beyond merely reducing costs for launching payloads. It could revolutionize travel within our solar system, making missions to Mars, asteroids, and even the outer planets more feasible and cost-effective. If successful, this could open up new markets for space exploration, including asteroid mining for resources, which could generate substantial economic returns. Additionally, improved propulsion technology could shorten travel times, enhancing the safety and feasibility of long-duration missions. This may lead to increased investments in space exploration from both government and private sectors. On the flip side, there are economic risks associated with investing in fusion propulsion technology. The long development timelines, coupled with the technical challenges that still need to be overcome, mean that investors may face uncertainties regarding the ultimate success of the technology. Furthermore, competition from other propulsion technologies such as ion drives or solar sails could impact the market viability of fusion propulsion. These alternatives may require less investment and offer quicker returns. Another critical consideration is the regulatory landscape surrounding nuclear technology. Fusion propulsion systems will likely face stringent regulations and safety concerns, which could increase development costs and create additional barriers to market entry. This regulatory environment will need to evolve to accommodate such innovations, ensuring safety measures are in place while also fostering an environment conducive to technological advancement. Moreover, the potential societal benefits of fusion propulsion, such as enabling humanity's expansion into space, are profound. When we think about design concepts in the context of space exploration and astronomy, it's fascinating to see how these ideas have evolved over time, reflecting our growing understanding of the universe. One notable design concept is modular spacecraft, which allow for different components to be added or removed depending on the mission's needs. This approach not only maximizes efficiency, but also provides greater flexibility in mission planning. For instance, NASA's Orion spacecraft, designed for deep space missions, incorporates a modular design that can be adapted for various objectives, whether it's crewed missions to the Moon, Mars, or even beyond.
Another innovative design concept is the use of inflatable habitats for astronauts, which could revolutionize how we think about living in space. These habitats are lightweight, compact, and can be deployed quickly, making them ideal for missions to places like Mars, where constructing permanent structures may take years or even decades. Companies like Bigelow Aerospace are already experimenting with inflatable modules, which provide the necessary living space for astronauts while being easy to transport and set up. Additionally, bioregenerative life support systems are crucial for long-duration space missions. This design focuses on creating closed-loop systems that recycle air, water, and waste using plants and other biological processes. These systems can sustain human life for extended periods, reducing the need to transport supplies from Earth. Research from organizations like NASA has shown promising results with experiments conducted on the International Space Station, demonstrating how plants can thrive in microgravity and contribute to life support. The design of spacecraft is also heavily influenced by the challenges posed by radiation exposure in space. Designers are now integrating materials and technologies that can provide better shielding from cosmic rays and solar radiation. For example, researchers are exploring the use of polyethylene, known for its effectiveness in blocking radiation, as a primary material for spacecraft walls, especially for missions beyond low Earth orbit. Furthermore, the design of space telescopes has dramatically advanced our understanding of the universe. The Hubble Space Telescope, launched in 1990, is a groundbreaking example of how design can enhance our ability to observe distant galaxies, nebulae, and exoplanets. The design considerations for Hubble included its location above the Earth's atmosphere, which allows for clearer images, as well as its modularity, which has enabled servicing missions that have extended its operational lifespan beyond original expectations. In addition, the concept of swarm robotics is gaining traction in space exploration. This design idea involves using multiple robots working together to carry out tasks, which could prove invaluable for complex space missions. In the quest for advanced space travel, scientists and engineers have proposed several fascinating designs for fusion-powered spacecraft, aiming to harness the immense energy produced by nuclear fusion, the same process that powers the stars. One of the most discussed concepts is the fusion rocket, which could use fusion reactions to propel a spacecraft through space at incredible speeds. This design often envisions a system where a fusion reaction creates high-energy plasma, which is then expelled at high velocities through a nozzle, generating thrust. Theoretical designs, like the Direct Fusion Drive, DFD, are particularly noteworthy as they combine elements of both fusion and electric propulsion, potentially allowing for efficient travel to distant destinations such as Mars or even beyond. Another captivating concept is the use of inertial confinement fusion, where small pellets of fuel are compressed and heated to the point of fusion using powerful lasers. This could lead to spacecraft capable of firing bursts of energy to produce thrust, allowing for rapid acceleration and deceleration, crucial for space missions. The National Ignition Facility in the United States has been a pioneer in this area, conducting experiments that could inform future spacecraft designs. Designs that incorporate magnetic confinement fusion, where magnetic fields are used to contain the hot plasma produced during fusion reactions. This type of spacecraft would utilize advanced superconducting magnets to create a magnetic field strong enough to keep the plasma contained, ensuring the reaction continues efficiently while also providing the means to convert the fusion energy into usable thrust. The concept of a magnetoplasma dynamic engine represents this approach, which could potentially offer continuous thrust, allowing for long-duration missions without the need for large amounts of fuel. Moreover, researchers have considered more exotic ideas, such as the use of fusion-powered sails, which would utilize the energy produced by fusion reactions to propel a spacecraft using the pressure from emitted particles or radiation. This design could enable spacecraft to travel vast distances without the need to carry heavy fuel supplies, relying instead on the energy generated by the fusion process itself. A particularly intriguing proposal comes from the Project Orion concept, which, while initially focused on nuclear fission, has inspired ideas for fusion propulsion. The basic premise involves using directed energy from fusion explosions to propel a spacecraft forward, creating a unique mechanism for thrust. Although this concept raises significant safety and engineering challenges,
its potential for rapid interplanetary travel captures the imagination of many in the space exploration community. As we look to the future, the promise of fusion-powered spacecraft represents not only a leap in technology, but also new opportunities for space exploration. Integrating a fusion engine into a spacecraft's overall design involves several complex considerations, as fusion propulsion represents a significant leap from conventional chemical rockets. First, the spacecraft structure must accommodate the fusion reactor, which, unlike traditional engines, requires a robust containment system to manage the extreme conditions of a fusion reaction. This containment typically involves magnetic fields or inertial confinement methods, so the design would need to include strong magnets and advanced materials that can withstand intense heat and radiation. The weight and size of the fusion engine compared to chemical engines would also be a factor. Fusion engines could be heavier, but they offer much greater efficiency, so the overall design may be streamlined to optimize for this. Moreover, the craft's thermal management systems must be enhanced to handle the heat generated by the fusion process, so integrating radiators or heat exchangers into the exterior design would be essential. The propulsion system would need to be connected to the spacecraft's power systems, as fusion engines generate electricity, which can be utilized to power onboard systems, instruments, or even to provide additional thrust through electric propulsion methods. The integration of the fuel supply for fusion, which typically involves isotopes like deuterium and tritium, also presents challenges. Storage tanks must be designed with safety in mind, and they need to be incorporated into the spacecraft's layout efficiently. In addition, the cockpit and control systems would require modifications to handle the unique operational characteristics of fusion propulsion, including monitoring the reactor's stability and adjusting the fusion output for thrust. This means that the interface for pilots or automated systems would need to be developed with new telemetry and control algorithms. Furthermore, the spacecraft's trajectory planning would take into account the different thrust profiles of fusion engines, which can provide continuous thrust over long periods, allowing for more efficient travel to distant destinations, such as Mars or even the outer planets. Additionally, safety protocols must be established, as the fusion engine poses different risks compared to traditional engines. Engineers would need to design fail-safes and emergency systems to prevent radiation leaks or reactor malfunctions. Finally, the integration of a fusion engine would also have implications for the spacecraft's mission profile, potentially allowing for missions that previously seemed impractical due to time constraints, opening new avenues for exploration in our solar system and beyond. Superconductors are playing a crucial role in the development of fusion propulsion systems, which are seen as a potential game changer for space travel, allowing for faster and more efficient journeys through our solar system and beyond. At the heart of fusion propulsion is the idea of harnessing the power of nuclear fusion, the same process that fuels the stars, including our Sun, where light atomic nuclei bind to form heavier nuclei, releasing immense amounts of energy in the process. This energy could be used to propel spacecraft, allowing them to travel at a significant fraction of the speed of light, which is far beyond what is currently possible with chemical rockets. Now, superconductors, which are materials that can conduct electricity without any resistance when cooled to very low temperatures, offer several advantages for fusion propulsion systems. For one, they can create very strong magnetic fields that are essential for containing and controlling the hot plasma needed for nuclear fusion in a fusion reactor. The plasma must be kept stable and confined away from the walls of the reactor vessel, and this is where superconducting magnets come into play, as they can generate the strong magnetic fields necessary for this confinement without wasting energy, unlike traditional magnets, which lose energy due to resistance. Translates to longer missions and the ability to carry more payload. Researchers are actively exploring materials that can become superconducting at higher temperatures, which would make them easier to use in practical applications, including space missions. Current superconductors require cooling with liquid helium, which adds complexity and weight to any system. However, if high-temperature superconductors can be developed and utilized, it could revolutionize the design and feasibility of fusion propulsion systems, allowing for lighter spacecraft and more straightforward cooling systems. Moreover, the development of fusion propulsion systems powered by superconductors could lead to breakthroughs in long-duration space missions, such as manned missions to Mars, or even beyond, to the outer planets and their moons. The combination of high efficiency and the ability to sustain thrust for extended periods could significantly reduce travel times, making interplanetary travel more practical and opening up new possibilities for exploration of our solar system. Overall, superconductors are an integral part of the ongoing research in fusion propulsion systems, which could pave the way for a new era in space exploration. When we think about the vastness of space, one interesting aspect that often comes to mind is how we test and implement new technologies for space exploration. These processes are critical to ensuring the success of our missions. Testing in space exploration typically involves a series of rigorous evaluations, as engineers and scientists must simulate the conditions of space on Earth, which can be incredibly challenging given the extreme environments encountered beyond our atmosphere, with temperatures that can plunge to nearly absolute zero and radiation levels that can be harmful to both equipment and humans. One common method of testing is the use of vacuum chambers, where scientists can recreate the vacuum of space, allowing them to observe how materials and instruments behave without the influence of air pressure. Additionally, thermal vacuum tests are conducted to assess how spacecraft systems will handle the extreme temperature fluctuations of space, moving from the intense heat of direct sunlight to the frigid cold of shadowed areas, which can vary drastically in a single orbit around Earth. Moreover, testing does not stop on the ground. Once a spacecraft is launched, it undergoes further evaluations during its journey. For example, the Mars rovers are equipped with numerous sensors that continuously monitor their systems, sending data back to mission control, which helps engineers make adjustments or troubleshoot any issues that arise. This real-time data collection is crucial, as it allows for immediate responses to unexpected challenges, which are common in the unpredictable environment of space. Implementing new technologies often involves collaboration between various organizations, including government space agencies like NASA, private companies, and international partners, which can lead to innovations that push the boundaries of what we can achieve in space exploration. For instance, the development of reusable rocket technology has significantly reduced costs and increased access to space, allowing for more frequent missions and a greater variety of experiments to be conducted. Another fascinating aspect is how testing leads to the implementation of life support systems, which are essential for human spaceflight. These systems must be meticulously designed, tested, and validated to ensure that astronauts have a safe and habitable environment while in space. This includes everything from oxygen generation and carbon dioxide removal to water recycling and temperature control, all of which must function flawlessly in the harsh environment of space. The International Space Station serves as a prime example of this, where ongoing research helps improve life support technologies, not just for current missions, but also for future endeavors, such as manned missions to Mars. In addition, one of the most critical factors in testing and implementation is the importance of redundancy testing. Fusion propulsion systems on Earth, before taking them into the vastness of space, involves a complex interplay of scientific experiment considerations. To begin with, scientists can utilize specialized facilities known as fusion test reactors, which mimic the conditions necessary for nuclear fusion to occur. These reactors, like the ITER project in France, are designed to create and control plasma, the hot, charged state of matter where fusion reactions can occur. Researchers can conduct various experiments to understand the behavior of this plasma, how to contain it, and how to harness the energy produced for propulsion. In addition to large-scale facilities, smaller experimental setups can be used, allowing for more controlled tests of different fusion propulsion concepts. These smaller facilities can focus on specific components of the propulsion system, such as the magnetic confinement method, where powerful magnetic fields are employed to keep the hot plasma stable, or inertial confinement, which uses lasers to compress and heat fusion. Each of these methods offers unique insights into how fusion can be effectively harnessed for propulsion. Moreover, computer simulations and advanced modeling
systems. By simulating various scenarios, scientists
identify potential issues and optimize designs. These simulations can help determine the best materials for construction, the most efficient fuel types to use, and the overall design of the propulsion system, which is vital before any physical testing occurs. Conducting experiments on Earth also involves rigorous safety protocols, given that fusion reactions, while not as hazardous as fission reactions, still produce high-energy particles and radiation. Researchers must ensure that all safety measures are in place to protect personnel and the environment. This includes creating containment structures, using remote handling techniques, and ensuring that any radioactive materials are properly managed. The development of subscale models, which are smaller, less powerful versions of the intended fusion propulsion system, allows for hands-on testing without the full risks associated with a full-scale system. These models can be tested in various environments to study their performance, durability, and efficiency in a controlled setting. The data collected from these tests is essential for refining the designs and making necessary adjustments before moving forward to larger, more complex systems. Collaboration with international space agencies and research institutions can also enhance the testing of fusion propulsion systems, ensuring that the technology progresses toward practical implementation in space missions. Space to expand beyond the confines of our solar system. The potential of nuclear fusion propulsion technology holds the key to unlocking faster, more efficient travel, revolutionizing how we explore and utilize space. With further advancements in research, testing, and safety protocols, this technology could dramatically reshape humanity's future in space exploration. The collaboration of scientific teams across nations, pooling resources and knowledge, will be crucial in making this vision a reality. While there are still many hurdles to overcome, including the development of advanced containment methods, fuel handling, and cost-effectiveness, the rewards could be monumental. The ability to explore distant planets, moons, and even other star systems mastering this technology. As we advance in understanding the principles behind fusion energy, its application in space exploration will become more feasible and practical. In conclusion, nuclear fusion propulsion could open up new frontiers in space exploration, making missions to Mars, the outer planets, and even interstellar travel more achievable than ever before. The future of space travel is looking brighter, faster, and more sustainable thanks to the promise of fusion energy. The race to develop this technology is on, and with continued innovation and collaboration, humanity could soon take its first steps toward becoming an interplanetary species. In the quiet of the courtroom, the tension was palpable. The audience, holding their breath, awaited the moment that could change everything. As the defense lawyer rose, his voice steady but filled with conviction, he addressed the judge. "Your Honor, we stand before you today not to deny the facts, but to seek the truth in its purest form." The prosecutor, a seasoned attorney known for his unyielding approach, shot back with a piercing gaze. "Truth?" he scoffed. "What truth can there be when a man's life is hanging by a thread? The truth is, this man took the life of another without remorse, and now we stand at the precipice of justice being served." The judge, a stern figure, raised his gavel. "Order in the court," he commanded, silencing the room. The defendant, a man who had lived a life of violence and deceit, sat quietly, his face a mask of stone. His eyes flickered briefly, catching the gaze of his lawyer. A silent exchange of understanding passed between them. In this moment, it wasn't about right or wrong, it was about survival. As the trial progressed, witness after witness took the stand, their testimonies painting a grim picture. The murder was not a spur-of-the-moment decision. It had been premeditated. The victim, a well-known figure in the community, had been targeted for reasons that remained shrouded in mystery. But the defense wasn't giving up. They had one final piece of evidence to present, a crucial piece that could turn the tide in their favor.
The tension in the courtroom heightened as the defense lawyer called their last witness to the stand. The witness was a former accomplice, someone who had once been involved in the crime but had turned. State's evidence in exchange for leniency. Their testimony was the last hope for the defense to sway the jury's opinion. "I didn't kill him," the witness stated, been revealed. The courtroom, once filled with tension, now buzzed with whispers and uncertainty. As the recess ended and everyone filed back into the courtroom, the defense and prosecution were both on edge. The stakes had never been higher. With the new revelation, the trial could go in any direction. The future of the defendant now rested on a single thread of truth, one that could either unravel or solidify his fate. The potential of nuclear fusion as an energy source is extraordinary, but it's crucial to understand that while the technology is still in its developmental stages, the environmental and ethical challenges are substantial. While scientists are optimistic about the future of fusion energy, it may take decades before it becomes a viable energy source, not only for space exploration, but also for sustainable power generation on Earth. During the research and development phase, other breakthroughs could emerge that may yield cleaner energy solutions, benefiting both space missions and life on Earth. The future of nuclear fusion holds great promise, but careful consideration of its risks, resource acquisition, and technological development is essential to ensure the responsible and sustainable application of this potential energy source. As nuclear propulsion systems for space exploration are explored, the possibility of dramatically reduced travel times to distant planets and moons raises new challenges. The deployment of such technologies could revolutionize space travel, but the safety concerns, particularly regarding the potential for catastrophic accidents, cannot be ignored. A failure during launch or operation of a spacecraft powered by nuclear technology could result in the release of radioactive materials into the atmosphere, creating long-lasting environmental damage and health risks to both humans and wildlife. Furthermore, the long-term implications of using nuclear power in space must be carefully evaluated. The potential for contamination of celestial bodies, especially those that might host life, introduces a moral dilemma. Should we risk polluting pristine environments like Mars or Europa with nuclear technology, potentially affecting the ecosystems and our ability to study them in their natural state? This raises fundamental ethical questions about our responsibility as explorers and whether we should prioritize scientific curiosity over the preservation of other worlds. Another significant ethical issue revolves around the governance of nuclear technology in space. The Outer Space Treaty of 1967, signed by major spacefaring nations, prohibits the placement of nuclear weapons in space and emphasizes that space exploration should be conducted for the benefit of all humanity. However, the interpretation and enforcement of this treaty can become complicated, particularly when it comes to the use of nuclear materials for peaceful purposes, such as powering spacecraft. The militarization of space through advancements in nuclear technology could lead to geopolitical tensions as nations compete for dominance in space exploration. The ethical considerations extend to the societal implications as well. Public perception of nuclear technology remains polarized due to the association with past disasters such as Chernobyl and Fukushima. This fear and distrust can influence funding for research, the development of nuclear propulsion systems, and the public support for space missions that utilize nuclear power. Scientists and policymakers must carefully navigate these concerns, ensuring that the benefits and risks of nuclear technology are communicated transparently to foster informed public discourse. Finally, intergenerational ethics must also be considered when making decisions regarding the use of nuclear technology in space. The long-lived isotopes used in nuclear reactors could remain hazardous for thousands of years, creating a legacy of radioactive waste that future generations will have to manage. This concern brings the issue of nuclear waste management to the forefront of discussions about the future of nuclear energy
in space exploration. When comparing the waste produced by fusion versus fission, it's important to understand the fundamental differences between these two processes. Fusion, the process that powers the sun,
involves the merging of light atomic nuclei, such as hydrogen isotopes, to form heavier nuclei, releasing significant energy. In contrast, fission involves the splitting of heavy atomic nuclei, like uranium or plutonium, into lighter elements, also releasing energy. The waste produced by both processes must be carefully evaluated when considering byproducts are typically helium and neutrons. Helium is harmless and poses no environmental threat, while the neutrons produced can interact with surrounding materials. These interactions can create some radioactive materials, but fusion reactors are designed to minimize this waste, and the radioactivity of the resulting materials is short-lived. This makes the long-term storage and disposal of fusion waste far less complicated than that of fission. On the other hand, fission generates a variety of radioactive isotopes, many of which are highly toxic and have long half-lives, meaning they remain hazardous for thousands of years. The waste from fission reactors includes isotopes like cesium-137 and strontium-90, as well as actinides such as plutonium, which can remain dangerous for tens of thousands of years. Managing this waste requires secure storage solutions, often deep underground. To isolate it from the environment and human populations. The debate surrounding the safety and efficacy of current disposal methods remains a contentious issue. In terms of volume, fusion waste is much smaller, as the reaction produces less overall waste. The materials that do result from the process are generally less hazardous. This efficiency makes fusion an appealing option for future energy generation, as it could reduce the burden of waste management associated with nuclear power. Additionally, fusion fuel can be derived from abundant resources like water for deuterium and lithium for tritium, making the sustainability of fusion energy higher than fission, which depends on finite uranium and plutonium supplies.